Take a walk past the historic UK buildings that have stood for centuries, and you will see facades built from limestone. It is one of the most enduring foundational materials in the history of architecture. Limestone is a biological sedimentary rock. It forms from the accumulation of organic debris, ancient corals, algae, and crushed shells that have gathered over millennia. But sourcing this material exposes a vulnerability in the construction industry. To the naked eye, different grades of stone look identical. Even seasoned building managers and architects can confuse a basic porous limestone with a dense premium marble. A surface-level visual inspection is an unreliable way to judge a rock's true geological identity and structural strength. To understand how it will perform, we have to look inside the rock. That brings us to Oolitic Limestone. It is a durable, premium subcategory of Calcarenite. Calcarenite is simply a limestone made out of sand-sized grains of calcite, typically tiny fossils or shell fragments. However, Oolitic limestone avoids the flaking and weathering issues that affect standard sedimentary rocks. To understand why it survives where other stones erode, we have to look past the quarry and the building facade. We need to examine the microscopic architecture of the stone itself. The macroscopic endurance of our oldest cities depends on a specific geometric arrangement visible only at the microscopic scale. Look closely at this 3D cross-section of Oolitic limestone. You won't see the jagged, chaotic fragments found in other sedimentary rocks. Instead, you find a tightly packed matrix of perfectly round spheres known as ooids. The name derives from òoion, the ancient Greek word for egg. Under a microscope, the non-crystalline structure resembles millions of tiny eggs cemented together into a solid, uniform mass. Most sedimentary rocks are formed from the chaotic, random compression of whatever debris happened to settle on the ocean floor and get squished under pressure. Consistent spherical geometry does not occur through random compression. It requires a specific kinetic geological process to take shape. That process requires specific conditions: shallow, warm, and clear marine waters heavily saturated with dissolved calcium and magnesium. As a single shell fragment or sand grain is caught in the intertidal movements, it begins tumbling along the seabed. As it rolls, the grain extracts calcium carbonate directly from the surrounding ocean water. It precipitates calcite, wrapping itself in smooth concentric coats, layer by layer, until it forms a sphere. The final diameter of that ooioid grain serves as a direct geological record. It tells us how long that particle tumbled in the waves before finally being buried by other sediment depositions. Millions of years of oceanic kinetic energy and chemical precipitation are ultimately trapped and preserved within the spherical geometry of the stone. When we shift our focus from the microscopic spheres back up to the massive scale of a quarried block of stone, we see exactly how that ocean chemistry pays off. Most standard sedimentary stones have a built-in flaw called cleavage. Cleavage is the tendency of a rock to break cleanly along specific parallel structural planes or layers, creating natural weak points that fracture unpredictably. Take a look at this side-by-side structural comparison. The physical stress that would snap a standard layered rock right along its fault line behaves differently in oolite. The tightly packed matrix of uniform spheres eliminates cleavage entirely. Stress distributes across the stone, allowing it to adjust to temperature changes without splitting. Because it lacks those fragile layers, the stone holds a distinct physical advantage. It can be cut, shaped, or struck from any angle, without compromising its structural integrity. That omnidirectional strength is what allows a modern stonemason to carve intricate, multi-directional shapes, like this lion head gargoyle, that would shatter lesser stones. It also gives the material a resistance to environmental erosion, which is why it is utilized for outdoor pavers, heavy-duty blocks, retaining walls, and historical monuments. But identifying true oolite limestone from lower-grade rocks is beyond the scope of a standard visual inspection. Because they look so similar on the surface, sourcing your materials from verified industry experts is mandatory. Whether building a modern backyard space or preserving the walls of a historic city, architectural endurance relies on a microscopic geometry shaped millions of years ago by ancient ocean tides.